Hi everyone, this video is on question 11 of exercise 9G of PO2. So we have a function, basically a curve that has parametric equations x and y in terms of t, and in part A we want to find an expression for dy dx in terms of t. So since it's parametric differentiation, we first differentiate x and y with respect to t separately, and then we use those and find dy dx, which and now I'm going to show that. So dx dt is equal to x is cos t, and cos differentiates to minus sign, so we have minus sine t, and dy dx is equal to sine differentiates to cos, but remember that here is sine 2t. So first we differentiate first of all we write down a half. Now we differentiate 2t, which differentiates to 2, and then we differentiate the outer function, which is sine of something. So sine differentiates to cos, therefore we have cos 2t. And this can be simplified. Also, I mistakenly wrote here dx, it's actually dt. So dy dt is equal to cos 2t. Now we want to find dy dx. So dy dx is equal to dy dt divided by dx dt. Dy dt is cos 2t, and dx dt is minus sine t, and that's dy dx in terms of t. Now part B. Part B says that find an equation of the tangent to the curve at point A where t is equal to pi over 6. Okay, so we have done many questions like this. It should be very familiar to you by this time. When we want to find the equation of the tangent at a specific point, we need two things before we can find the equation of the tangent. We need the gradients at that point and also the coordinates of the point. So in this case, we can first find the gradient at point A, and in order to find the gradient, we just need to substitute the value of t into the expression of dy dx. That gives us the gradient at point A. So when t is equal to pi over 6, then the gradient can be found by substituting pi over 6 into dy dx. So 2t, so t is pi over 6, 2 times that is pi over 3, and then in the denominator we just have minus sine pi over 6, and that gives us the value of minus 1. So minus 1 is the gradient when t is equal to pi over 6 at point A. Now we want to find the coordinates of point A. So in order to find that, we substitute the value of t into the equations of x and y, because when we substitute them, that gives us the coordinates of point A at t is equal to pi over 6. So first, well, the first one, x is cos t, so x is equal to cos of t is pi over 6, and the similar approach for y is that half sine 2t, so half sine 2t is pi over 3, and we get root 3 over 2 for x, and for y we get root 3 over 4. So these are the coordinates of point A, root 3 over 4, and the gradient, as we found earlier, is just minus 1. Now we are ready to find the equation of the tangent, which is equal to, we can use the formula y minus y0 is equal to m times x minus x0. So substituting the values, y0 is root 3 over 4, m is just minus 1, and x0 is root 3 over 2. Right, we can see rearrange this. Y minus root 3 over 4 is equal to minus x plus root 3 over 2. then y is equal to minus x plus root 3 over 2 plus root 3 over 4, and simplifying the right hand side, minus x plus 4, and then we get 3 root 3 over 4. So this is basically the equation of tangent to the curve at point A. So that's the answer to part B. Okay, now let's do part C, which is actually the interesting part of the question. So it says we have two lines. Lines L1 and L2 are two further distinct tangents to the curve. So basically it's saying that we have two more tangents to the curve other than the one that we just found in part B. Given that L1 and L2 are both parallel to the tangent to the curve at point A, find an equation of L1 and equation of L2. Okay, just to show you a simple diagram, just to realize what's going on. So let's say this is the curve. It's not accurate by any means, just the curve, for example. And let's say that, or maybe it's not the best curve. Let me change that slightly. So let's say this is the curve, for instance. And in part B, what happened was that we just had a tangent at point A. So let's say this is point A, and this is the tangent, right? And we found the equation of that. Now, the other part is saying that there are basically two more tangents, two more lines L1 and L2, which are a tangent to the curve, and they are also both parallel to the curve at point A. So if let's just extend the curve a bit, and what's going on is that let's say this is point B, for instance, and this is actually line L1, for example, and this is point C, and this is line L2. And what's going on is that, as you can see, we have two more tangents to the curve at different points. So this is crucial. And all of them are basically parallel to the main tangent that we found in part B. So now the question is, find an equation of L1 and L2. So we want to find the equations of those lines. So let's see how can we find that. So before I begin, let me just remind you that parallel lines have equal tangents. So the tangent of line A, the line that passes through A, is -1. So that means we can immediately realize that lines L1 and L2 have tangent -1. But the other element is obviously knowing the coordinates of the point that the line passes through. So points B and C in this case, we don't have them. So the objective is finding the coordinates of points B and C so that we can find the equations of the tangent. So now the question is, how can we find the coordinates of B and C? Now, the most important step to answer part C is realizing the fact that I just mentioned, but in a more mathematical and algebraic way. Because what I just mentioned was that, which is more like a geometrical approach, was that, okay, so L1 and L2 have the same tangent as the red line, which is the one that we found in part B. So that means, they have the same gradient, which is -1. And now we need to find the coordinates of B and C. So now, how can that be translated mathematically or algebraically? Because what I'm just saying is effectively the expression for tangent, remember, the expression for the gradient, I don't know why I'm saying tangent. The expression for the gradient is dy dx, right? And we found that dy dx is cos 2t divided by minus sine t. So that's the expression for finding the gradient. Now we are saying that they all have equal gradients. So that simply means we need to find the specific values of t that allows us to find the coordinates. We just want to know, for example, what's the value of t at point B, and same thing with c. What's the value of t at point C? Because when we find the values of t at points B and C, then we can plug in the values of t into the equations x and y, and that simply gives us the coordinates at B and C. So now the objective is finding the values of t at B and C. So how can we do that? It's very simple. We just take the expression for dy dx and just set that to 0, minus 1. So the reason we solve this equation that dy dx is equal to -1 is basically because we already know that all of those lines have the tangent -1. So now the question is for what values of t. So by understanding that, the rest of the question just becomes a routine that you've already had that in previous questions of this exercise. So cos 2t over minus sine t is equal to -1. Now we just need to solve this equation in order to find the values of t at different points that I just showed. So cos 2t is equal to a cross multiplication gives us sine t. And in order to solve this equation, we just need to remind ourselves that using the double angle formulas, cos can be written as 1 minus 2 sine squared t is equal to sine t. So the reason I did that is I wanted to have each of these terms in terms of sine, so we can solve this equation directly. Now rearranging this gives us 2 sine squared t plus sine t is equal to -1. And we can use the technique of changing the variable to solve this equation. So we can say, let sine t be, let's just use a different variable, for example, u. Then substituting that, we have 2u squared plus u minus 1 is equal to 0. Now it's a simple quadratic. So after solving this quadratic, we are going to get two values for u. One of them is a half and the other one is -1. Now we go back, and because we said u is sine t, so we now have two equations, sine t, two trigonometric equations. Sine t is equal to a half and the other one is sine t is equal to -1. Okay, the next step is solving each of these equations. But before that, just remember that the values of t are greater or equal to 0 but less than 2 pi. So that's very important. So t is less than 2 pi. Okay, now let's solve the first one. Sine t is equal to a half. So we get pi over 6 as well as 5 pi over 6 for the values of t that are in the range in the given domain for t. And now for this one, when we have -1, this one is a slightly interesting, and it's simply it's simply 3 pi over 2, not minus, because it should be between the values of 0 and 2 pi. So these are the values of t, and the interesting thing that is happening here, which you might have already realized, is that for one of the values of t, we got pi over 6, which is what we were given in the question to begin with, right? So again, these three values of t are the values that the expression dy dx has a gradient -1. So we have already used this one in part B, and now it's the matter of using each of the other two in order to find the equations for L1 and L2. At this point, it's just very standard, because we can begin by when t is equal to 5 pi over 6, And then we know obviously the gradient for all of this is just -1. We just need to find the coordinates of the points that the line passes through, and then just using the equation of line to find the tangent. So when t is equal to 5 pi over 6, and substitute this into equations of x and y here to find the coordinates, we get minus root 3 over 2 for x, and y is minus root 3 over 4. And so as a result of that, when we use this equation of y minus y0 is equal to m times x minus x0, again, m is just 1 in all of these cases, that's the gradient. Substituting the points of x and y, we'll get the equation y is equal to minus x minus 3 root 3 over 4. So that's the equation for line L1. So the equation of L1 basically. Now the second case is when t is equal to 3 pi over 2, and in this case for the values of x and y we're just going to get 0. So in this case x is 0, y is 0 after substituting into equations of x and y. The gradient is again -1, so simply the equation of L2 is y is equal to minus x, which is a simple case. Okay, so that's it for this video. We now have found the equations of lines L1 and L2. Okay, thank you for watching.